Okay, so after that introduction, we proceed to construct the real numbers. So we go back to the construction of the real numbers, and this will be done using Dedekind cuts. So the idea is to construct the real numbers as a subset of the power set of the rational. Okay, so since we assume the rationals exist, we can start from that set, the set of rational numbers, and use a particular type of subset, or which we can define the natural operations of addition, multiplication, and order. Also, the order structure can be preserved and actually extends the notion that we understand from the rational numbers already. And in doing so, we'll achieve one more additional property, which is the least upper bound property. Okay, so we with the starting point is we assume, so as I said, recall the fact that we're assuming that the rational numbers have already been constructed. Have already been constructed. And that all the properties of addition, multiplication, and order are satisfied. So all the notions and all the properties that we're used to have for the rational numbers, we assume that the construction that happened before this course sometime using set theoretic tools make available for us all the properties that we need in order to proceed and extend the rational to embed the rational numbers into a larger structure called the real numbers. And keep in mind that at this point we still don't have real numbers, so we need to define something that will allow us to talk about real numbers. Okay, so in the book they introduce the very important definition. This is definition 8.6.2, if you want, and says that a subset of the rational numbers is called a cut if it satisfies the following properties. You name C1. First of all, it cannot be the empty set, and it cannot be the whole of Q. So it cannot be all of the rational numbers, and it cannot be all of it cannot be the rational numbers, all of them, and it cannot be the empty set. So it has to contain at least one element. In fact, as soon as it has one element, it contains every number that is smaller than that number. And that's the second property. So if we have that some rational number belongs to this set, then if Q is less than R, this implies that Q is in A as well. Okay, so that's the important proposition that needs to be satisfied. So if you have there's a number R in A and you have another number that is smaller than R, then it also belongs to A. The third property, third condition on the set A to be called a cut is that that you can, whenever you find a number inside A, you can always find a number that is bigger than that number still in A. So let me see. So this is the property. If R is in A, this implies that there exists S in A such that S is greater than R. This is referred to, so property C3 is referred, so let's see, so this is, should be understood as saying that A has no maximum or largest element. Okay, so this so these three conditions together define a cut. So if you find a set that satisfies all these three properties, it is a cut. And if it's a cut, then it must satisfy condition 1 to 3. So it's what we ask of a set in order to call it a cut. So one example of a cut is the following. So if this is very important, this is actually appears in exercise 8.6.1, and so if R is in Q, then CR defined as the set of all the numbers in Q such that these numbers are smaller than R. Yeah, that's a cut. Another type of cut that we encountered before, even though we didn't call it a cut because there was we hadn't defined that notion. So this will be example 1, and so it's slightly different set, but the definition. But the main point was the same. It's just that we want to think of the set of numbers whose squares are smaller than 2, but we're also going to include all the negative numbers. So in the same exercise, they include this very important cut. which has been with us since the beginning of the course in the motivation for the construction of the real numbers. In one way or another, because you know the square root of 2 is not a rational number. And so we consider the set of all the rational numbers that are either negative or whose square is smaller than 2. So just to avoid confusions here, just a small comment. In order to belong to the set, you need to satisfy this condition here or this condition, but it doesn't mean that you need to satisfy just one or the other. For instance, -1 satisfies that so this OR is not exclusive, so -1 is in T because -1 squared is less than 2. So one of the conditions is satisfied, but -1 is also less than 0. So both conditions are satisfied. So this, I mean, to check whether a number belongs to T or not, you just need one of them holds. Also, saying 1. 1 belongs to T because 1 squared again is less than 2, although 1 is not smaller than 0, so 1 is greater than 0. So the second condition is not satisfied, but remember in logic, so this proposition here being a number whose square is less than 2, or a number that is negative, in order for that to be true, just need one of them to be true. The other one can be false, and that's irrelevant. Okay, so these are examples of numbers that are in the set T. And this happens to be a cut. In fact, the property that it doesn't have a maximum follows pretty much along the lines of what we did before, when we showed that the set didn't, I mean, a related set where we didn't actually include all the negative numbers, but the proof is very similar. It doesn't have a least upper bound in Q. Okay, but even inside the set, the thing is, if you have a number whose squared is less than 2, you can approach 2 as much as you want by taking the squares. And so if you have a number that is in T, then you can always find another number whose square is actually closer to 2 than the previous one, and therefore is actually bigger than the first one. One piece of advice when we are working the out exercise, this exercise 8.6.1, is to note that if you define here this set T, but instead of asking for a strict inequality, you ask for just a simple inequality, that actually it's actually the same set, because you know that T squared can never be equal to 2 if T is a rational number. So those two sets are actually the same. So that may save you some time when you're computing things, and just realizing that. I mean, in general, if you had this set where just a set, I mean, if we define the set CR as a set of rationals that are smaller than or equal to another rational number, then that would not be a cut, because it would have a maximum. But R defining it would be the largest element. You will not be able to find something bigger than that inside the cut. So that's what's different about it. So in this case, when you're considering numbers whose squares are less than 2, the difference is that the squares, I mean, the squares being equal to 2, I mean, a square being equal to 2 cannot happen inside Q, so those two sets are the same. And in general, when you include that or equal, so as less than or equal to, that kind of ruins it for it to be being a cut, unless the equality is precluded to happen inside the rational number.